Hi everyone, in this video we are going to find the Laplace transform of a ramp input signal, also known as a ramp forcing function. Like we did for the step signal, let's draw our simple block diagram of a generic process model so we know what we are working with. When we convert everything to the Laplace domain, that includes our input signal, which can sometimes be known as a forcing function. So, knowing how to do this Laplace transform is very important. So, if you remember, the Laplace transform of a general time function is the following. And our input ramp signal is represented mathematically as a composite time function like so, which makes sense because at time 0 the ramp signal will begin to grow. So let's apply our input time function to the Laplace transform. This leaves us with the following. Let's remember that we can split up our integrals because we are only determining the area under a function. So by splitting it up, we are not actually changing anything. For this one, it is probably pretty apparent that we should split this integral up where the change occurs. So for us that happens at time 0. However, if your ramp forcing function looks like this, then you would simply have your integral from negative infinity to 2 and not 0. Since this is a compound function, it is a function made up of two or more equations, let's just go ahead and apply those input values, so 0 initially and t for any times greater than 0. If you're wondering why we integrated from negative infinity to 0 and not just started our Laplace transform at 0, I just wanted to show you why this is often the case. In practical problems, a time less than 0 really doesn't mean anything, so it only makes sense to start the integral after time 0. The left integral is going to go to 0, as we can move the 0 outside, and no matter what anything multiplied by 0 is going to be 0. Therefore, let's focus our efforts on a more interesting portion, where the ramp input signal turns on. So let's begin by taking the Laplace transform of our remaining integral. The bounds of the integral are going to be from 0 to infinity. Now be careful here. In our integral, we have two independent variable terms. Therefore, we need to perform integration by parts. The integration by parts formula is here, and we can use the acronym LAIT to remember what to pick for our u value. LAIT stands for logarithm, inverse, algebraic, trigonometric, and exponential. Whichever of the two terms appears first in the acronym, that is going to be your u term. Then we just need to find du and v like so. Applying these newfound values to our integral, we end up with the following. Now, before solving the left portion, let's solve the right integral. We can factor out the 1 over s, then we can take the integral of this remaining term. Applying our bounds to both integrals and multiplying through in the case of the right integral, we end up with 1 over s squared, which is the Laplace transform of a unit ramp input signal. Earlier I showed you how we would proceed if you had your ramp input signal begin at some time other than time 0. You would simply change the bounds of your integral and go through it the exact same way. But what would happen if your ramp input signal had some slope that wasn't equal to 1? Well, again, the solution is simple. In this step here, you would simply factor out the constant, that is, the magnitude of your input, your slope, and then you would proceed in the exact same way. So at the end, you would end up with a over s squared, where a is the ramp slope. Thank you for checking out this video, and I hope it helped your understanding of the Laplace transform of a ramp forcing function. If you enjoyed, please like and subscribe to support the channel. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.